the opportunity of being here. It's very nice city, very interesting workshop, discussing different things. So I will just present some results obtained in my group in Barcelona, in collaboration with a lot of peers, with many people. Mahanti Masia Strakarti here present, Robert Zilik from the University of Leeds, and Stefano Giorgini from Trento. So the outline would be first I am the third or fourth one speaking about dipoles, so I will skip some details. But in any case, I will insist on why it's so important to work now with dipolar interactions, which 20 years ago were not interesting in quantum systems, because there were not realizations of this. But now it's really very important. Some results about the dipoles in a plane with isotropic interactions. Then what happens when you tilt the angle and then you have really an isotropic interaction. I will show very nice results, I think, about the existence of a stripe phase in this system. And then I will end with some results which are unpublished about the bilayers setup, which is similar to the one that Stefano has discussed for the case of fermions. In this case, I will discuss about bosons with a nice finding of pair superfluidity in the case of bosons, which is somehow more new. So there are several quantum dipolar realizations, you know a lot. So for example, in the case of big gases, you have atoms with relatively high dipole moments, and also molecules. We are waiting for even more larger dipolar moments. And then also you have these spatial indirect excitons in which you have two quantum wells and you can have this dipolar interaction. So what's nice is that for our theoretical perspective is that the interaction between two dipoles is quasi-long range. It's not long range strictly, but it's quasi-long range in a plane. And also because it's anisotropic. And then it depends not only on the distance between the dipoles, but also between the angle between the vector that joins the two dipoles and the orientation of the dipole. And so in this case, the interaction is not always repulsive, but it becomes attractive, and then it's very funny to see what happens with the system. The strength of the dipolar interaction is normally quantified by this parameter, which relates this parameter, which takes into account the strength of the dipole interaction and the S wave scattering length, which is always present in the case of Bay cases. So this is normally achieved in the first one was chromium-52 with a magnetic dipole moment of 6 Bohr magnetons, which is not very large because this parameter then is only 0.16. So it was the first example, but not the best one. But what's interesting is that playing with Fesberg resonances, in this case, you can decrease the S wave scattering length and emphasize the interaction due to dipoles. So you can play with Fesberg resonances and enlarge this parameter. Of course, the stability is enhanced by using tight pancake traps into the geometry, because otherwise the system is unstable due to the effect head-to-tail attractive part of the interaction. We are waiting for polar molecules. Yesterday we learned about a new sodium-potassium molecule, which is promising to get an even larger D. In such a way as D squared here, we can arrive to really very intensive dipolar interaction. In this case, we can get 20 or 200 or even stronger. But yesterday we also learned that there are experimental problems to arrive to quantum degeneracy in the case of these molecules. So we have to wait a little more. There are also interesting proposals to achieve these high dipolar moments using Rydberg atoms, but really not achieved up to now. So in chromium-52, there is this interesting paper from Lahey where it is shown that playing with the Fesberg resonance, when the magnetic field approaches to this V0 plus delta, okay, you can practically reduce the S wave scattering length in such a way that you can see the effect of the anisotropy of the interaction. For example, in this case A, here, you can see that nearly the scattering length is in this case is nearly reduced. Okay, and then you can see the anisotropy of the interaction. The two-dimensional model is this one. You have seen it before. So you have a kinetic part, and then you have an interaction, which is in which intervenes the strength of the interaction. Then it appears also the sinus of alpha, which is alpha is the polarization of the dipole with respect to the perpendicular to the plane. And then this cosinus, which relates this angle here perfectly. Normally one uses reduced units, R0. Stefano has introduced these units. And then the only parameter that remains is this combination, the density times this distance squared. Okay, so this is the only parameter that describes the interaction. The methods that we use are fully microscopic, so relies just only on the Hamiltonian. There is not S-wave term, so there is not a hardcore interaction, so it's all completely dipolar interaction. And we have used essentially two methods, what is called diffusion Monte Carlo and this ugly name, path integral ground state, which is based on path integral but adapted to calculate properties of the ground state. Both methods are essentially exact for bosons, as it is the case, and only a statistical error affects the measure. Both are projection methods. I will not go into details. Okay, skip that. Normally one needs a model for starting the projection, and for starting the projection normally one starts with a Bill-Jastrow-Nosonov triwave function, which is built as a product of one body terms, two body terms, and you can count three body terms, etc. But normally we stop here. The two-body correlation factor useful in this case is just the solution of the two-body problem, where K0 is the modified Bessel function, and then it is cut at some distance, and then you introduce a phononic contribution to account for the log range of the interaction. And then in the case of the gas, you take just one for the one-body term. But if you want to describe a solid, you introduce some localization factors to the Nosonov style. Okay, so imposing that the particles are around a given size. This is similar to what Stefano has shown in this case for fermions. First, let me show some little old results about which is the physics of dipoles which are all perpendicular to a plane. In this case, the interaction is purely repulsive. It's much boring in the sense that it's just 1 over r to the third, okay, in a plane. And then what you get, essentially, this is the energy. You can calculate the liquid and the solid, and then you can extract which is the transition point. Okay, you make the double tangent Maxwell construction, and from here you get the phase transition. The coexistence zone is extremely small. This also was commented by Stefano, and the density is relatively high. Okay, so you need to arrive to a very high density to get this triangular lattice. The Lindemann ratio is also calculated and is given by this value. It's also interesting to know which is the condensate fraction. The condensate fraction, of course, this is at 0 temperature. At 0 temperature you can calculate the condensate fraction, it's finite. But you know that at finite temperature it is not more condensate fraction. In this case we are relying on 0 temperature. And we extract the condensate fraction just calculating the one-body density matrix and looking at which is the behavior at long distance. Okay? As expected, the condensate fraction decreases with the density, and it's really nice to see that even when the density is quite slow, the value is really small. Remember that in helium you have 0.10. So this is not very dense system, but due to the long range of the interaction, the deflection is really very large. That's nice to observe. So in this sense, it could be dilute, but not dilute in the sense of long range orbit. We have also studied excitations. Quantum Monte Carlo is not a good method for studying dynamics, but what we have made is to use combination with CBF theory, which is the theory developed for the study of for quantum liquids, helium-4 and helium-3, and even in nuclear matter. So the idea is just to write the dynamic response in this formula, okay, where this is the self-energy. I will not enter into details. So this is a long treatment of that. But what is interesting is finally, this S of q omega is written in terms of what is called the direct correlation function in diagrammatic analysis. which is related to the inverse of the static structure factor. That's the interesting part. So our idea was just collaborate with the people in Linz, which are expert on using this, and we introduced the S of k calculated exactly using the quantum Monte Carlo to extract the response of the system. And we see here what we obtained. This is the color density of the S of q omega. The points are what is called the Feynman spectrum. If the density is low, the response follows the Feynman law. But when you start to increase the density, of course, you start to see that the strength goes down. Okay. Here you have the points still are Feynman approximation, but you see clearly the emergence of the roton. This roton is not the roton that Stefano has shown by Luis Santos, because that roton was due to the instability in quasi 2D due to the formation of head-to-tail effect. In fact, this is just 2D, so it's barely repulsive. This is the roton like in helium due to the high density. Okay? Let's go to the case where the angle now is not zero. So we tilt the dipoles. We are still in the plane, but we tilt the angles, the dipoles, a given angle. Okay? We have to remain below the critical value. The critical value is this one, where it starts to appear an attractive component that will collapse the system. Okay? So we cannot surpass this value, but we introducing this tighter dipoles, we can see really the anisotropy of the system, and that's nice. For example, here I show what happens in the case of the radial distribution function in the two directions. So in the x direction, the interaction is softer, and in the y direction is stronger. Okay, and then you see how when the density starts to increase, and you approach the critical value, you see that the distribution of particles in the both directions are not the same. Okay, so anisotropy of the interaction introduces differences in the spatial correlations. This is even more clearly seen in the case of S of k. You know, S of k is not normally is more illustrative about the order of the phase. And you see that when the angle is quite large, you see clear difference between the structure in both directions. Okay? This is a reflection of the anisotropy of the interaction. That's nice to see what happens if you enforce that. So you imagine that you take an angle which is not far from the critical value, and you start to increase the density progressively. Okay? Here you can see snapshots from the quantum Monte Carlo of the system. And here you see S of k, okay, in both directions. Here you see more or less C at low density a gas phase. Apparently there is not a special order. If you increase to 128, you see clearly a big effect, but not still. You can see somehow lines here, but not really more apparent. But when you go really to this high density, 256, you see clearly two Bragg peaks here. Look at the scale, now it's logarithmic scale. And what you see is that the stripes appear in the y direction where the interaction is stronger. I don't know if you can see these lines. Okay, so it appears like a spatial structure in the y direction. This is even more clear looking at the distribution function. In grayscale, you see that when you arrive to this value shown before, and very close to the critical value of this angle, you see clearly the emergence of these lines, which are a reflection of the stripe phase. Okay, so the system organizes in these lines. This is also true for the case of the spectrum. So we have repeated again a calculation of the dynamic response using the CDF theory. Okay, and what you can see is that in this case is the less repulsive part, so x direction. And in here, you have the y direction. If you go to the extreme case, you see here in the softer part, a clear roton, but nothing special. But when you go to the y direction, you see clearly a roton that touches zero. And even you can see the emergence of the second roton. It's like a solid excitation spectrum. Okay, in the y direction, what you see is the formation of a crystal. So you have order in the y direction. This is the definition of the stripe phase. So you have a phase where you have a gas in the x direction, but you have order in the y direction. It's a funny phase. Here you can see how we identify the transitions. In this case, for example, from gas to solid, from gas to crystal, what we look at is which is the height of the main peak of S of k divided by the number of particles when you change the density. Okay? What happens is when you are in the gas phase, okay, this is nearly flat, but when you are right to a given density, there is a step here, and then it starts to increase. So this is the interpretation from a gas to solid phase transition of first order, because there is a gap here. Okay? This is also repeated at 0.2, 0.4, different angles, we see the same. So the gas to solid transition is of first order. In the case of gas to stripe, this new phase, you see that this peak is not abrupt, the change, but it's like a continuous transition. Okay? You can see the difference from here to here. It induces to think that somehow this transition is of second order instead of first order, from the gas to stripe phase. Okay? And in fact, this is the case. So we have made the analysis using finite size scaling. So we plot the S of k as a function of the density for different number of particles. Okay, and then we can see that all the curves collapse to a single one with a given set of parameters. This is indication of the second order phase transition. The parameters of the fit that leads to the second order phase transition, you can see we cannot distinguish between these two universal regimes. So it could be that this is a 3D Ising model or 3D XY. This is the exact exponents. We have some error here. So our results cannot be conclusive in that, but it's conclusive in the sense that what we have here is really a second order phase transition. This is quite special because at zero temperature it's not so easy to see a second order phase transition. But we believe that this is second order. Even if we increase the angle to 0.58, we see again the same. Okay? And the scaling parameters are more or less the same, except the critical density. Okay? So it seems that the curves will collapse to a given one. So this is the result that we have at present for the phase diagram. I think it's quite funny. So here we have the angle up to a critical value in which the system becomes unstable, and here we have the density. Okay, so we have transitions from gas to crystal, which are first order, from gas to stripe, which are second order. From crystal to stripe, we believe that they are first order, but we are not completely sure, because for us it's very difficult to calculate at this high density, so we are not conclusive on that. But look at it's even very nice because there is cases in which at a given density there is a double transition. Look at, for example, I don't know, 350. Okay, here when the angle is small, you have a crystal. Okay, then crosses to a gas. This is very strange. So when the angle becomes larger, it means that the system, as a mean, is less repulsive. The system goes to a gas, and then if you surpass this value, you finish with a stripe. So we have, for a given density, you have a double transition, which I think is fine to see this. And also the novelty of this stripe phase, because to my knowledge is the first clear signature of the stripe phase that have been announced for Fermi systems. But in Fermi systems in a plane, when all the interaction is merely repulsive and not anisotropic, Stefano didn't found this stripe phase because the stripe phase is due to the anisotropy. Otherwise, it does not exist. Good. The second part is related to the bilayer. Bilayer is made by, so you take two-dimensional planes and you put dipoles perpendicular to the plane, and you make a separation edge. It's very similar to what discussed previously, and it could be also similar to these excitons separated by two planes. This is the Hamiltonian. There are interactions which are repulsive in this plane, repulsive in this plane, And then what is nice is that between the upper and down dipoles, the interaction is essentially attractive. And this is very nice because that introduces a lot of physics. You can see here which is the up-down potential. So you have a well here which is attractive. And as Stefano has commented, we are in 2D, so we have always a bound state. Okay? So then it's interesting to see if the system wants to be molecular phase. We have used different trial wave functions for sampling. I will not enter into details. I show here how the energy changes as a function of the interdistance between the planes H. Okay? You see that when the distance is small, remember that there is an attractive component of the interaction. It dominates, and then the system is in this kind of phase. This will be the limit of it. I will not enter in that. But then when the H increases, the energy goes down. So there is a transition between what we will call the molecular phase and the atomic phase. Okay?
That you're in each layer is a liquid or a solid?
No, we have a gas in both liquids, in both places. So the density is not high enough to see this. No. So what we have studied to determine the superfluid properties of the system is to calculate the one-body density matrix and the two-body density matrix, defined right here. We calculate that in Monte Carlo, and we obtain the condensate fraction of the atomic part by looking at which is the behavior of the one-body density when the distance goes to infinity. And in the same way, we can study if there is a molecular condensate fraction when determining the long-range behavior of the two-body density matrix. So here I show some results. The molecular condensate here is obtained as the limit that I showed before by subtracting the part coming from the one body. So this will be the intrinsic molecular condensate. Okay? And also we define what is called the superfluid response that was introduced by Pupillo and others in the study of the same setup but with the lattice. So this is the difference between the Windig number of the upper and down layers. So it's the difference essentially between the superfluidity of the first layer and the second layer. What you see here is that there are clearly two regimes. In this regime there is not atomic condensate. The atomic condensate is zero because in fact what you have are molecules, and then at a given interlayer separation the atomic condensate starts to increase to a given value. Okay? The behavior is very similar to the one of the superfluid response. So it's zero and then grows up. So this is the order parameter of the transition. So there is a transition that leads from a situation where you don't have atomic condensate to a situation where you have atomic condensate. And also what's nice to see is that when in this part you don't have atomic condensate, but you have molecular condensate. So you have, if you want, pair superfluidity. So you have the case of composite bosons which behave as a new boson which is superfluid. Okay? So you see a system where you see clearly pair superfluidity, but in a continuum, because the first prediction was in the case of the lattice. Here is a continuum phase. So we see clearly the existence of a pair superfluid phase in the continuum setup. This is completely new for bosons. What?
Yeah, just the case that was discussed.
Yeah. Yeah. That's very nice. And the second observation is that if you look at here, the intrinsic molecular condensate is not there is at least a region in which is not zero. So you have simultaneously atomic condensate and molecular condensate. Okay. So it seems like a remaining pairing effect, but for bosons. Okay. So this is, I think, the first case that I know where is a regime in which you have atomic condensate and kind of pairing, but pairing of bosons, which is, I think there are papers, all papers that discuss that. One of these is this Kobe from 1969. There were hypotheses, but never checked. The similar conclusion arrived at high density, so it's a similar picture. No, this is high density. Also, we have calculated the gap in the system you see that the gap is finite when you have this pair superfluidity, and then it arrives to 0 in the case of atomic superfluidity, as expected probably, okay? And confirm the existence of this phase transition. This is a preliminary phase diagram which separates the case of this molecular regime of pair superfluidity from the atomic superfluidity. The line is a crude estimation, but I will not enter into discussion. And I think I am arriving to the end. So our conclusion is that we observe a gas-solid phase transition in the isotropic case, and isotropy in titled dipoles induces the emergence of a new quantum phase, a stride phase. So this is, I think, the first signature, clear signature that at 0 temperature we can have stride phase in a continuum, and also that in the bilayer setup it allows for the observation of pair superfluidity without lattice. The previous study, the study was made in the lattice by Sabafi, Naini, and Guido Pupillo, and others. And I think with that, I end my talk.
Questions?
Yes.
I have one about this continuous transition between the gas and the charge, the stride phase, let's call it. Because you said that according to the numerical calculation, you cannot tell whether the case is in favor of XY universality mass arising. But in principle, looking at the symmetries that are broken in the charge density web, you could make at least an educated guess about what. Because if you had rotational symmetry broken in the gas, for instance, or not. So the rotational symmetry is broken in the gas or not?
Probably yes.
In that case, you are left with an icing when you go from the gas to the charge density wave. Otherwise, you are left with the next one.
Thank you for your observation. Very good.
Jordi, just want to understand a couple of things a bit more clearly. You showed one slide where you had a non-zero, simultaneously had a non-zero condensate of the atomic and the molecular. Then I saw a phase diagram which seemed to have the two phases separate. And I'm just trying to picture, particularly, I mean, can you have interpenetrating condensates that, do they affect each other?
What we think is that there is only one order parameter, which is the atomic condensate, because this is 0 in one place and finite at the other place.
Yeah.
Instead, the molecular condensate is never 0. This is our, so we cannot be used that as an order parameter of the transition.
Okay.
This is what we think, and we agree, I think, with that, with the lattice calculation. So there is only one order parameter related only to the atomic part.
And so when you had your phase diagram, and you had a separation there, what was I...
Well, this is a little schematic.
Yeah, sure, but just in principle.
Yeah, what we make here is, these points are the Monte Carlo points, are crudely estimated where I see, okay, more or less looking at which point it starts to change. Okay? But it's, I agree with you that it's a little crude.
Well, it's interesting.
But it's difficult to get better. Huh?
Yeah.
We have fighted a lot with this, and
Right.
We are not able to see any more precise. Yes.
Thank you.
Just to this point, how does this depend on the size of the system that singles and molecules coexist?
It's not depending a lot. So we have changed the size of the system
In the infinite limit,
within our possibilities. This is a very heavy calculation, and we have not seen appreciable effects of the size. But we cannot be conclusive. When you make Monte Carlo, it could be that remains some finite size part, but it has to be small. This is our appreciation.
Does the thing that you call the molecular condensate fraction, is it sensitive to phase coherence between adding a molecule here and taking it away over there?
Yes, very sensitive.
So don't you think that means you have long range order there? Maybe you just isn't that something real?
I think it's real. Yeah, because you have, in fact, they are molecules. In fact, they are molecules.
Why is it not an order parameter? Maybe you're always in an ordered state.
Yeah, but what happens is that if you increase a lot the distance between the layers, of course, formally there is always a bound state, but you lose that because they are in the interaction in the intra layer.
but just having molecular states for two particles doesn't guarantee you have coherence when you have many pairs, right?
Yeah, but we calculated the long-range order of the two body density matrix, and if you see a plateau, there is
At T
coherence.
equals zero.
There is a coherence. Otherwise, you will not see a plateau. You will see it decaying to zero.
If you want to go away, eat the system.
Fit the system. Yeah, that would be interesting to see, for example, what happens with the transition in both sides.
That's a very good question to choose one here. So, how large is really the system you look at?
The largest we have most used 100 and something particles. Okay.
Per layer.
Per layer.
So 200
Yes. It's more or less in the limit. And within these limits, we have not been able to see scaling.
Right.
So remember that when you made it before, we were discussing. So that's related, I think, to the technical issues in the simulation. We were not able to see.
So this could be an effect of this thing, sort of the paradox. But you say that.
No, I think it's a technical issue related to the way in which you calculate the condensate fraction, which is, depends a lot on the size, the specific determination of the condensate fraction, and then trying to see what happens in our particles. We have tried, but nothing conclusive.
More questions? Everybody needs coffee desperately. So let's thank all speakers this afternoon.